Let me just get a sip of water before. Okay. Good morning or good evening or good afternoon, depending on when you are listening or watching us. And thank you for being here in the another material business episode. My name is Monica Hernandez and I am your host with Infinity Growth. And I have a very special guest, Hugo Julien. Is he and I have been working for a long, long time. And thank you for accepting the invitation. He has a lot of knowledge of many different areas. So today we're going to touch base in one of them. Thank you, Hugo, for being here.
Mi placer. Mi placer.
So Hugo currently works as at CEP Forensics as forensic engineer and HJC Consultants as a senior consultant in pressure installations of all kinds. He has held several positions of responsibility in different departments, such as quality, production, and engineering assessment, and has been applying the ASME API codes in very in-depth fascination since 1998. I witnessed that when we worked at Shell. Due to his expertise in interpretation and practical application of codes, Mr. Julien is a highly sought after consultant for pressure equipment and storage tank fabrication, inspection, repair, and all sorts of engineering assessments. He is also a skilled communicator, able to easily define and solve problems. Mr. Julien has also been giving seminars on pressure vessels and piping since 2004 as an ASME instructor. He's also a certified API 571 and a CSA W178.2 Level 2 inspector. Finally, he's a CSA B51 associate member since 2017. Hugo, thank you so much for being here.
It's my pleasure, Monica.
So let's begin.
Yes.
When I asked you to come to the podcast, I wanted you to bring all that side that you have access now as a forensic engineer. And because we have been talking to many people in the podcast, and we know that sometimes we don't make the best decisions, right? When we have to do material selection or when we have to maintain equipment or we operate equipment. And that brings, and we all know that brings failure before estimated life or at the end of life, or it brings some sort of anything, right? So maybe let's start by defining what is that a forensic engineer term.
He's a kind of fool. He's it's pretty niche. This is the kind of engineering field that you will be able to see things that you will never seen before normally as a normal engineer, let's say. So in other words, we are waiting incidents. We are waiting. It's sort of way to see it. We are waiting incidents of all kinds: explosion, leakage. We can maybe face some different kind of contract issues. Different kind of conflict between two parties. We have a contract to do. We have a problem of interpretation of the contract. We thought that it was that, and the client say no, you say yes, and you need lawyers to do that kind of stuff. So they need me sometimes to do these kind of interpretations. So in other words, it's always conflicts, incidents, bad days. Okay, bad human errors. I think it's the main. It's pretty important to insist on that. It's never done by magic. There is always human somewhere. So in other words, my mission is to understand what happened and find out the reasons why the incident came into place. So it's not easy sometimes because there is a lot of emotion. Sometimes people don't want to say to me that it was their fault. So I need to find out by asking questions, by finding out or investigating different kind of documents. The quality of the documents, it's pretty important, by the way, guys. If you give me some documents that it was not well done, in quality documents, it will not help me to find out the real answer of the reason why the incident occurred. And of course, it will bring me in a bad direction. And if the direction is to say that this guy is the bad guy, and in fact it was not the case. This is can be very horrible. And I can say that you are the bad guy, and finally, because of the quality of the document, it was not that bad guy. I didn't find the real bad guy. So the quality of the document needs to be pretty well done. And of course, yeah, I don't know if I'm answering your question, but at the end of the day, I'm weighting incidents. This is a forensic engineer.
So it's almost like a forensic, like in real life. Someone murders someone, and then the investigator comes and finds out who
Yes.
that murderer is. So in these cases, what happened? And I hear you said, and you made emphasis on the word human error.
Yes.
So is that what you're finding most of the cases?
Right. It's 100% of the time. 100% of the time. It can be, name it. It can be different kind of subjects, such as you have a process to deal with chemicals, temperature, pH, oxygen content, all these kind of chemicals that we need to carry or transport from A to B, or putting in the pressure equipment. So now it's time to talk about the appropriate material to deal with these kind of chemicals. If it's not the appropriate materials, of course, it's written in the sky that you will have issues, and you will find me in your way somewhere. Forensic
And I
engineer.
will find you.
So it can be the welds, the heat affected zone. It can be whatever you can imagine related with the fact that the material has not been well chosen. And the other question is, okay, let's say that we are operating the equipment after 10 years. 10 years, we can see a leakage. So the question is it good 10 years? Is it reasonable lifetime for a pressure equipment? So 10 years, probably it will be no, probably. It can be yes for another context, but it's rare that it's a yes. Or maybe 25 years. What about 35 years? Okay, Monica, you don't react. Maybe 45 years. Is it good for pressure equipment? It depends on a lot of context, of course, to be able to answer this kind of question. And it's part of the forensic engineering. We need to answer these questions because the lawyers want to see that, to be able to negotiate with the other parties, to say to these guys, hey, 45 years, it was not very, very impressive for that pressure equipment. So probably you did an error 45 years ago by choosing this kind of material for that service. So this is a good example here. It can be whatever you can imagine. It can be the maintenance. This is another bad guy in maintenance. We are doing a perfect design, great material. The manufacturing process has been well done, great documentation, quality documentation, very professional. And then we operate the equipment without any inspection. Or the inspection has been done, but it's not clear. It was not very professional because we didn't took the time to understand all the damage mechanism involved. We didn't took the time to choose the appropriate NDEs, a non-destructive examination, to find these the risk of damage mechanism. If it's a crack that we need to find, because there is a risk of crack, and we are not choosing the NDEs to find cracks. It's not exactly what is the purpose of an inspection program. So it can be that. And the mission of the forensic engineer, of course, it's to go back and say, okay, what can be a good inspection plan for that context, and compare it with what they did, and what is the frequency of these inspections, and what about the output of the inspection, and what they did with the output of the inspection, results. So it can be tricky sometimes because there is a lot of gray zone. So you need to be careful by choosing your words in your report. If I'm saying that it's a bad guy, but I need to be sure that it's the bad guy.
Mhm.
So sometimes we it's not no, not sometimes, it's always difficult to point people, you know.
For sure, because you're also, like you said, it, we're working with emotions
Yes.
and people that took decisions, and who wants to be blamed? Nobody wants to be
No,
blamed,
no, no, nobody
and
wants to be blamed. Yeah,
yeah,
and
for sure.
especially 25 years after the fact. Let's say, just imagine you're doing a design right now today. You're sealing a drawing, and do you know that in 25 years you can receive a phone call
Mm,
from whatever lawyer or whatever, and you receive a letter from that guy and saying to you that 25 years ago you did a bad design,
mm,
and this is where you did a bad design, and you need to fight to prove that that design was good to go, and you did another stuff pretty bad, which is the maintenance, or the the other subject, Monica, by the way, it's the operating windows, or, operating windows of the equipment. And if let's say that the maximum pressure is 100 psi, and you choose a set pressure of your safety relay valve at, let's say, 200 psi, and you operate it at 150 psi or whatever. So it's pretty easy to say that it's not exactly what was the purpose of that pressure equipment. An explosion occurred. We called that the designer 25 years ago, and of course, it will be easy for that guy to prove that the equipment was not operated according to this is limitation, let's say, which is the
mhm,
maximum allowable working pressure. But the very bad subject that I'm seeing a lot of time, it's the fatigue aspect. So
mhm,
we have a maximum operating pressure of 100 psi, let's say, on the nameplate of the equipment, but the owner operated with different kind of batches. Let's say the process is in the batch process, so we are removing the product inside the vessel to 0 psi, and then the next day 100 psi, and then the next day 0 psi. So we are fluctuating the
mhm,
pressure inside. So the original designer didn't know that, for example,
mhm,
that they will use it for a fatigue aspect. Let's say the damage mechanism will be fatigue, and he didn't design it for that purpose. And the crack occurred, leak, or maybe bad worst case scenario, an explosion. So who's responsible of that?
mhm. For
Is it?
sure.
Yeah.
And so you're bringing a lot of really important aspects, and is this, the social responsibility of PNG and the people that are sealing those designs, those drawings. That responsibility never ends, because if something happens down the road, like you said, 25 years in the next 25 years, then probably you'll have to go back and find out a way to defend yourself, and you might not even have those files anymore. So
Yes.
it is very important to be thorough and to have all that backup uh, for a long time. So that's one of the very good things. But you're also mentioning, so let me ask you this. A failure can occur for many bad decisions. So we can take a bad decision at the design, or at the fabrication or operation or maintenance, or yeah,
Installation
pretty
also,
much
it can be installation
installation, yeah,
issues. Yeah.
fabrication and installation. So which one is the one that you're seeing the most? In which
Maintenance.
of those is maintenance? Wow.
So and operation. Yeah, there is a battle between the operation and the maintenance. In other words, it's post-construction activities.
Uh-huh.
Probably not 80% of the time, it's related with bad operation and or bad inspection. Because in other words, We purchase something like that, pressure equipment of all kinds. It can be a boiler, by the way. It can be a storage tank. We didn't talk about that. It can be a steel stack. It can be whatever you can, a pipeline. Okay, it's always the same story. So we are doing the design at the first day. We are doing a great design. It's done according to the standard. Let's say. But of course, all your assumptions as a designer, by the way, just want to open something quickly. If you want to do assumptions, don't keep it in your mind. Put it
Oh
on the
no, it has to
paper.
be documented. Yeah, for
Yes,
sure.
yes, because 25 years later, if we are going back to your design, it's not written anywhere that you didn't take in consideration the fatigue aspect or the seismic, or it can be the crosswind, or it can be just imagine all the load cases that you can imagine. You didn't take in consideration these load cases, but it was not important. I put it on the paper that it was not important for you at that time. So you need to be clear. There is a weakness at that specific location, to be honest, for the design aspect. But it's rare that the design didn't well is the cause of the incident. The real cause is we are not operating the equipment according to the original design, and we don't inspect it because we don't know how to inspect it, or we are delegating the task to an NDE subcontractor. Do an inspection. I don't know exactly what I need, but do it. And then you're doing it, bring a report to you, and you don't know how to read the
Assess.
report, and you don't know what to do with the result of the report, and you put it in the file and you forget it. Normally, these guys are not engineers. Normally, I'm not saying that it's not always the case, but they are technicians. They are doing the job that you want to do. And I'm talking about the ultrasonic examination. I'm talking about maybe magnetic testing. I don't know exactly, but it's not structured. They don't know the real story about the vessel. They are doing their best with their knowledge, but they don't know the damage mechanism involved. They don't know anything about all these
And
kind
they
of
don't
things.
have to because they're not paid
Yes,
to know it. That is why you have people like us
yes,
doing and telling them this is the mechanism and this is how you should be inspecting to get that mechanism. And you touch a point that is really important. It's you don't like even today when we are called into plants of all sorts. A lot of the times, all the inspection plans are based on ultrasonic testing, and I mean thickness ultrasonic testing,
mm,
which we know is good for general corrosion, and that's about it.
mm,
So the chances for you to pick a pitting or the chances for you to even pick some other mechanisms are very rare with that technique. But I just wanted confirmation. So 80% of the time
mm.
is post construction. That is a lot.
Yes,
It's
yes,
a
yes.
lot.
Well, it can be, as mentioned, the post-construction activities can be related with the original design, such as, for another example, let's say pressure piping connected to your pressure vessel, on the nozzle. So
Mhm.
let's say the pressure piping with thermal expansion, because of the weight of the piping system, will transfer bending moment, torsion, or axial force to the pressure equipment. You know what
Mhm.
I'm talking about here?
For sure.
So normally, the original designer, don't include these external forces in this final design for whatever the reason. It can be bad reason, can be good reason, but the main reason it's the owner. The owner shall, and I'm insisting on this shall, not should, not may, shall communicate these kind of load cases, uh, like the other ones that I mentioned, which is the fatigue aspect, which is the seismic, the crosswind. So all these load cases can be very obvious because your pressure equipment will be installed in a seismic area, but the designer will probably not include it because the owner didn't request it.
Mm-hmm.
And it can be a sort of issues. Of course, if the post construction activities later will justify the 80% of the time of the incidents, maybe the original design, if we have a lack of load cases included, can contribute to the future of this equipment.
For sure.
But my point here, the owner, I'm talking about to you guys, all the owners that listening right now. More and more, you will see in the ASME codes. Well, people do you think people knows what is an ASME code? Okay,
For
here in the
sure.
podcast. Okay, so American Society of Mechanical Engineers, all these standards used for building all these pressure equipment, pressure piping. More and more, you will see in these future editions, or if it's not right now, the importance of the owner to describe his needs when it's time to purchase these equipment. And the rationale behind this is because we want that owner to understand what he bought and to be able to structure, of course, an inspection program, and he will know more and more than ever how to analyze the output of the inspection program.
Mm-hmm.
So if in other words, if he's not participating at all to the project and he's put aside because he don't have the time, because of whatever the reason, he don't have enough knowledge, it doesn't make sense because
Mm-hmm.
he will stay with the equipment, not the other subcontractors. He will stay. He will walk the line every day. His offices will not be far away from the pressure equipment. So he will be exposed to the danger every day. So
Yeah,
he shall be involved in the beginning to the end of the service life of these equipment.
for sure. And I know that you work in different industries, right? So you have like you receive cases from various different industries in your plate. Which ones are the ones that you guys see the most?
Uh, Not the refineries. But yes, of course, they have incidents, but it's not the kind of guy. They are very well structured. They have a lot of good people, engineers. They have the team is in place. They know the danger. They
Mm-hmm.
are very very exposed to that. And to be honest, I don't receive so much files from these guys. I want it, but it's it's not the case, and it's okay. And it's okay. Now, all these smaller businesses, it's always smaller than refineries, and so it can be a storage tank terminal. It's a lot of different kinds of storage tanks somewhere, and then we take it for granted, all these storage tanks.
Yeah.
And we have pressure piping connecting all these storage tank, but this is the kind of places where it's not very good what we are doing at these specific places. For example, 2 weeks ago, I received a file for a
Mm.
bitumen storage tank here in Quebec, and your listener are localized all around the world.
They are.
Monica? Okay, so
They
Quebec
are.
is a province in Canada, and I have received a bitumen storage tank, 180 feet of diameter. Just imagine the size of that storage tank. 25 years of operation. And it was the first time they did an inspection, an API 653 inspection inside the storage tank. 25 years later, there is no damage mechanism, to be honest. It's 350 degrees Fahrenheit of operation, catalytic protection for the floor. It's very warm enough to avoid any corrosion under insulation. It's there is no clear damage mechanism, so it's okay to do an inspection every 25 years. But to do so, you need to remove all the bitumen inside. Imagine the amount of letters inside that tank. So, and you have a coil on the floor.
Yeah.
So the coil you will have a conflict to be able to inspect the floor with that coil. The coil is zigzagging everywhere. So they did an inspection. They did an inspection, and they have decided to use only something like 0.01% of the surface of the floor for inspection. 0.01%. Okay, just imagine the amount of percentage we are talking about. It's not very, because you need to clean it. You need to remove the bitumen on the surface of the floor. So they did very fast, and then they say to the owner, okay, it's good to go. It's good for another 20 years. 20 years, it will be good for another 20 years without any other inspection. So they put back the bitumen inside. Few weeks later, they have seen bitumen under the floor. The bitumen was leaking everywhere, so they decided that they didn't have any choice to do it. They decided to stop the operation of this huge storage tank, and by any chance they had another empty tank not far away, so they were able to transfer the product and the other storage tank. After investigation, maybe I can show you my screen. It's really neat. It's a real bad story. Do you see my screen right now?
It's coming up. Yeah, I can see it now.
Do you see my well here?
Oh,
this is the floor.
God.
This is the floor. This is a lap joint floor. So it's the minimum requirements of API 650 in 1998, which is the edition date of API 650, the code of construction used for building that storage tank. So just imagine 180 feet of diameter, bitumen at 350 degrees Fahrenheit in it. So if you remove it during winter days, so you're shrinking the storage tank, it will shrink. Mm-hmm. And then if you go back with your bitumen inside, you push by increasing the temperature of carbon steel. And by just doing one cycle, a full cycle of thermal expansion, that weld defect here, do you see it?
Yeah.
Well, it's an overlap. Okay, they call that overlap. Not good. No code of construction will accept that overlap. So this is the complete section here with the bad weld. Here it's not so bad. Here it was not so bad. We have a peak stresses here. But at that specific location, only something like 12 inches long. And you can imagine 150 feet of storage tank. So there is a lot of weld on the ground.
Of course.
Only that specific location was not well done in 25 years ago. So for the inspector, API 653 inspector, it was not easy to find, of course, with 0.01% of inspection. So in other words, there is no chance that you will see that. So because of these stresses, secondary stresses of thermal expansion, when you rise the temperature again, so here at that specific place, a crack was observed, and then the bitumen leaked at that specific location. So who's gonna pay for that? Who's responsible of that? Is it the inspector or the manufacturer of that storage tank 25 years ago?
It is whoever wrote that specification. How come 0.01% of inspection?
Yes, there can be another debate. Is it good enough? But is it probably maybe it makes sense to do it in the context? But at the end of the day, it's probably the two person. I didn't complete my investigation yet, to be honest. But it's a kind of example of stuff that you will need to do when you do your design. But the designer is not responsible of that, of course, because he's doing drawings and he's sealing the drawings and he's hoping that the weld will be well done by the manufacturer. Mm-hmm. But here it's clearly a bad manufacturing process. The welding was not well done. Not clear if he was thinking about his girlfriend or the welder. there is a clear human error at that specific location. The inspector at that time, 25 years ago, was supposed to see these kind of stuff. obviously didn't see it. And of course, 25 years later, we hope that we can find it, but it's not good engineering practice to say that we will do 100% of the surfaces of the floor. It's
Of
not good
course.
engineering practice. You can't do that. We have a coil. You cannot ask the owner to remove the coil, clean the complete vessel, do your inspection, and reinstall the coil after that. It doesn't make sense. You will not have any job as an inspector. Probably
Of course.
you will be too expensive. So where is the balance between inspection and good inspection and to face these kind of example or reality? So probably it's not easy to answer, but obviously the manufacturer was mainly 90%, let's say, of that file will be probably the manufacturer, and
Mhm.
we will go back to the manufacturer 25 years after the fact.
Mm.
So yeah, it's a sort of example of stuff that can happen sometimes. But can you remind me your original question, by the way, Monica? Um,
In which, because we've spoken about the industries and now we were speaking about in the processes. So you see the most of the damage afterwards, after, well, this is a case where you showed us. And thank you for showing those examples because a picture and it it's more than 1,000 words, we say.
yes, yes.
So it really shows us the idea behind it. So thank you for sharing. Do you have any other examples that
Yes.
are
I have another bad
visual?
another example who killed somebody. You want to hear about, a Netflix series, episode 1, episode 2,
Yeah.
a murder, a real murder. I'm sorry. My dog is coughing right now. I'm sorry about that.
No worries.
So I have a real example that somebody has done. Do you see my screen?
We do. Yeah.
This is a report. I can show my report because it's a public report. It's the health and safety authorities in here in Quebec, CNESST, which is, if you're speaking French, CNESST. So these guys mandate me after somebody has died because of an explosion of a pressure equipment. This is the equipment that we are talking about here.
Hmm.
So this equipment is a temporary installation. We are a it's a sand blaster, they call that, sand blaster. So they are putting sand inside, compressed air, and we are sandblasting some structure to remove rust and to be able to paint it after. Here it was a bridge in Quebec. So they installed the compressor, as you can see here, Solaire, the sandblaster. And during the day or during the operation, you have found a leak on that manhole, a small leak. Okay, so that specific manhole here, it was leaking. So they have ordered a gasket to be able to replace it. And then the next opportunity, the sand was pretty low. You need to open this quick opening on the top here, put the sand inside. They have decided to change the gasket at the same time. But
Hmm.
these guys didn't do that in their experience. It was junior operator, never did that in their experience. First time. So they did their best, in other words. So you know how it works, these manuals?
Yeah.
Maybe I can show. Oops, maybe I can show you this picture right here. This is the way to go. So we have an old brown shape. We have a cover that you put inside, and we have these two clamps, and you have the gasket inside. So if you have to deal with pressure, the higher pressure you will have, more compression you will have on the gasket.
Hmm.
Okay. So they have changed the gasket with a new one, reinstall the clamp as the best as they could, obviously, and they put the pressure back. And few seconds later, the cover went out of that hole, and went out and passed through an highway, okay, like a bullet.
Oh my God.
and nobody has been killed in the car, but one guy was walking in front of the vessel. And when the compressed air has been released, something like 120 psi of compressed air, the guy has been pushed on the structure, and he died immediately because his surface, his face was completely destroyed.
Oh,
Okay,
wow.
so he died because of that. That not the cover didn't touch the guy, but the blow of the
Yeah, just
compressed
the
air,
energy, the
the
energy
energy
that was
deployed.
released.
Yes, exactly. So if I'm going back to this picture right here, so the equipment was here. Do you see the traces on the ground?
Yeah.
So that equipment, that huge equipment full of sand. So just imagine the amount of weight that we are talking about here used to be installed at that specific location. And then when the cover has been removed by pressure, just the power of the compressed air getting out of there pushed the vessel something like 10 feet from the original location. So just imagine the amount of force and huge energy that we are talking about here. After investigation, Monica, do you know what happened?
No.
It's Earth. No, it doesn't make sense. You will say to me, but it's 12 by 16 inches, the size of these manholes, as you know, probably.
Yeah.
They have installed a cover of 11 by 15 feet inside the 12 by 16 feet.
No.
Feet, I'm sorry, inches. It's not feet, inches. So the cover was smaller, obviously, than the O-brown shade, original O-brown shade inside the vessel. So obviously it doesn't make sense. It's not supposed to be installed there, because if you understand the history of these ASME code, it used to be the manuals of these pressure equipment used to be 11 by 15 feet. I'm sorry, inches.
Inches.
And now since 2001, or since the beginning of this century, the code has changed to 12 to 16 inches, because probably American people are bigger than ever, so they have decided to increase it. But for whatever the reason, it's not clear in my investigation why, after we have installed a smaller cover inside the manhole. It was not clear. Nobody were able to explain me that, but obviously it was not the original cover. When they did the pressure vessel, the brand new vessel, on the data report, it was written that the cover was 12 by 16 inches. Now somebody has changed it for whatever the reason, and when you have installed it, they didn't center, the cover exactly at the center of the 12 by 16 inches, and they have changed the gasket thicknesses. It used to be very thin, very rigid gasket, and you have decided to change for a rubber gasket, thicker gasket. So the cover, if you don't install it on the middle of the hole, and it's thicker, the gasket, and it's, the rubber material, it's not as rigid as another kind of material. So the cover moved because of gravity, probably, and then a breach probably has been created, and the compressed air was able to get out of there. Plastically deform the cover, because the cover cannot get out of that hole because it's inside. So you need to deform the cover, plastically deform the cover, to be able to get out the cover of there and release the complete energy from the vessel here. So here is clearly it's a human error. From different kind of human errors, somebody in the past changed the cover to a smaller cover. The guy who did the job that day, no experience at all. They were not able to say, "Oh, there is a problem with that cover. There is something strange with that cover. There is no so much movement in that cover. I cannot center that cover. Probably it's not the appropriate cover for the nozzle. So I will stop to do the job. I will not do it. I will ask questions. There is something wrong with that." No experience, so they don't know anything about that. They did their best, And also, by the way, the safety device was not, the set pressure was higher than the pressure equipment, but it's not the reason why the explosion occurred. But it's another example of bad installation. Well, the set pressure was 200 psi, and the design pressure of the vessel was 150. So it's, well,
We have a
but
lot of room
it's
there.
not the explanation of the story. And the installation was not according to our regulation here in Quebec, in the province of Quebec here in Canada. So we have rules, and this installation was not according to the rules. But it's not the explanation of the explosion, but it's just other kind of subjects that can maybe explain some other kind of incidents. So that, in other words, that installation was not appropriate for the service, and it was written in the sky that the problem will occur pretty soon. So is it a good example, Monica?
Oh, wow. It's a fantastic example of many things that went wrong. Not only the change of, yeah, you can see how it really, you
Yeah.
shouldn't be able to do that.
No, you can't do
Hmm.
that without pushing
Yeah.
on the other side with compressed air. So just imagine it's crazy. People don't realize it probably, but the amount of energy ready
Hmm.
to be deployed inside these kind of equipment, it doesn't make sense. If you can maybe sit on my chair and see all these kind of stuff, you will realize the danger. Monica, it's not a joke, but when I'm driving my car, when I see a big truck, carrying liquefied natural gas, or uh, propane or whatever,
Hmm.
I don't like
Any
it.
of those compressed things.
I don't like it, so I'm driving faster to get out of the
Fast.
area of the truck. But it's my neighbor has a propane storage tank. I don't like it. I'm not using compressed air at home because I prefer electrical tools, because compressed air, I don't like it, because I've seen too much in my life. I don't want you to sell all your pressure equipment at home, but you need at least to follow the manufacturer requirements. When you have a compressed vessel at home, there's a maintenance to do, they call that.
Mhm.
So you need to drain it, because the water will be trapped inside, and you need to inspect it every year with ultrasonic examination. Probably people don't do that.
I don't think anyone does that. And this is a really good example of many things that went wrong. And like you pointed out, not only it wasn't sit down like it was supposed to be, not only the PSV was not labeled or was not rated
Mm.
for the service. So it is like that Swiss cheese picture that the HACCP people, or the safeguarding people, shows us all the time, that we don't want all those holes in the Swiss cheese to align, because then an incident will occur. And this is exactly the case. So many
Yeah.
things could have gone wrong before, but it's just at this time everything aligned, and then unfortunately that person is killed.
Or really injured, or yeah. Do you want another example for maybe just for
For
fun?
sure, for sure, just for
Another
fun.
file, but it's not industrial example. It's a water heater.
Okay.
Everybody has a water heater
Yeah.
at home. So where's your water heater right now, Monica?
It's in
In
the
your house.
basement. It's in
Okay.
the
Are
basement.
you above the water heater right now?
I am.
Right, exactly above? Really aligned with your water heater right now?
Not me, but like let's say the kitchen is
Okay,
right
so
above.
stay there. Stay where you are. You're not in danger. So just to see my screen right now. So it used to be under the stairs, the water heater. The water heater explode, pass through the stairs, pass through the roof, and arrive to the neighbor 100 feet away from that specific location here. 100 feet, it's like how many meters? It's something like 40 meters. I don't know.
Like 45 meters, yeah.
45 meters. So what happened here? Here the water heater was 11 years old. So do you know that every 10 years we need to change our water heaters? It's supposed to be like that proactively because it's it can be the all the devices can be damaged. So it's a sort of maintenance, let's say. And the water heater was 11 years old, so I'm 1 year above 10 years. And what happened? It's the thermocouples, all these heaters. There's a mechanical device open the circuit for electricity and close it and open it and close it and open it, and then it stay closed for whatever the reason, and the heater, heat the water, and we are during the night, so nobody was using water, and the temperature rise until we reached the point where the bottom head, which is a concave head inside the vessel, so we are pushing on the external surface of the head, so the head was not, it was the weakest point of the vessel, and the bottom head exploded, as you know, and the end of the story. So what happened with the safety device? We have a safety device. What happened? I don't know, Monica, because the safety device has been destroyed in the story here. And because it's on the upper section of the water heater, the safety device. So obviously the safety device didn't work, and it's the purpose of the safety device. So it was a problem of design, or it was a problem of maintenance. It was a problem of I don't know exactly what happened with the safety device, but obviously everything was aligned for a catastrophe that day. But it's pretty rare, by the way. People, don't be afraid of your water heater. This is very rare that you will see that kind of stuff. But it's an example of pressure equipment that we have in our house, waiting for releasing energy. Let's say here it was steam, because obviously we warm up so much a temperature that the water transforms in steam, and the volume of the vessel went up, and the energy needs to go somewhere. So another example of my days.
That's incredible. And I know that we are supposed to check that safety device on
Yes, it's true.
on the heaters, and it is very rare we do that. And
we are supposed to inspect the cathode, anode. How do you anode inside the vessel. So we need to remove it sometimes to double check it if the anode is still there. Nobody does that. We are supposed to drain the vessel. Who's doing that?
That's very and that's basic maintenance, So it's a potential issue that we have in everyone's houses, because we all like our showers to be warm, right?
Yes. So nobody's doing that. It's the reason why the insurance company now come with this requirements, which is 10 years. Because if we were maintaining these water heaters all the time, probably it will be 20 years of operation, because you're changing the anode inside, you're draining the vessel, you do your stuff to increase the duration life of operation life of the vessel. But because nobody is doing that statistically, thank you. Statistically speaking, it's 10 years. Because we don't do anything about that. So it's reason why.
And that's so sad, because that is not sustainable. We are talking in the podcast, we are talking a lot about sustainability, and then how we can make these things last better, or have another life in mind, or how we can reuse it, and then yet we are seeing that what we are in need, where we are implementing to protect ourselves, is something that it is not probably half life of that vessel, just because
Exactly.
we are not doing the due diligence.
I can
It's a
maybe
call for
talk about.
action, I guess.
Yeah. Yeah. I have a lot of different kind of example like this. I don't know how many minutes we have,
We
how
are
many
almost done
days we have.
here, but we'll bring you back for sure for another. Like, we're gonna do a series, like you said, like the Netflix. It's gonna be called the Material Business
Okay. Okay.
series.
Yeah. Part two, part three, part 26. Yes. Episode one, sub point 1.1, 1.2. Yes, we can do that if you want.
For sure. So since we are at the end of the time, what is your message for the audience?
But please help me as a forensic engineer to do my job. In other words, documentation, quality of your documentation, every assumptions, every thoughts, every observation, every pictures. That's the most important thing. And if you don't do that, it will be a mess to do our investigation. And also, it will be a mess to protect yourself against whatever
A
can
lawsuit.
happen. If you
Mm-hmm.
don't have any documentation, it's easy for me to point my guns in your direction.
Mm-hmm.
You cannot fight against that because you didn't document anything. Engineers, please. Yes, another message is professional engineers. We need these guys. We need these guys somewhere, everywhere. The design aspect, on the maintenance side, the inspection program, interpretation of the results, choice of the materials, of course, for the process. We need these guys. Of course, a professional engineer cannot be good in every field of expertise. So we have a code of ethic code saying that we can't accept tasks that we are not good to do. But we need professional engineers in the process to reduce the risk of incidents. I have observed a lot of time documentation without the existence of these professional engineers. So everybody are designing stuff, and they think that they have the knowledge to challenge the results, and everybody can be a designer somewhere. Everybody can do interpretation of the inspection results. But when a professional engineer comes to play in the team, I realize that there is less risk of incident. But I'm not saying that it's for sure you will not see any incidents if you have professional engineers. I'm not saying that we are God. I'm not saying that we have the answer of every questions. I'm not saying that, but there is lesser risk to see incidents. And more in the ASME codes and the regulations, you will see the requirements to have a professional engineers
Mm-hmm.
somewhere. And we can see that in the latest edition of the ASME Section 8 Division 1 for pressure equipment as an example. If you deal with a seismic or a fatigue or a final element analysis, you shall have a professional engineer involved in your design. So it's an example. Here in Quebec, we are, I don't know if you know CRN, Canadian Registration
Yeah.
Number. For people outside Canada, if you ship a pressure equipment here in Canada, we need to challenge your design. We need to double check your calculation, your drawings before giving you an authorization to build your vessel for the Canadian market. And before the professional engineer was not requested, now it's requested. We shall
Wow.
see a seal of a professional engineer on the drawing before giving you any authorization to build your vessel. So the future is going in that direction, and it makes sense because we have seen so much incidents,
Mm-hmm.
and we want to reduce them. Of course, it's our mission.
Of course, of course. And you have already the body that is enforcing that, and we have already the professionals that are in there. So why don't we use them? So it makes sense that we go in the direction of using someone that can stamp, because that is kind of your guarantee, right? That you have someone that is looking at it in a total way, because they know they are responsible. They know they will have social responsibility, like we spoke at the beginning, towards what they are doing. So it makes sense.
And we have an obligation to receive continuous training
Mm-hmm.
every year as a professional engineer. So we have the obligation to be, let's say, aware of the last technologies, or the last
Mm-hmm.
revision of the code, or we have the responsibility to keep training open every year as a professional engineer, to keep our permit to practice.
Mm-hmm. Exactly. Exactly. Well, Hugo, thank you so much. It's been a pleasure bringing you in and sharing with the audience. I'm sure everyone will super enjoy this, especially because you showed so many examples, visual examples. So people that are listening Spotify or Apple Music can go and check on YouTube, because there is cool pictures out of this. Thank you so much for being here. And once again, for the audience, thank you so much for growing and sharing, and then keeping us doing what we like to do. Hugo, thank you so much, and we look forward for, we'll call it the next episode.
Okay, okay. My pleasure, Monica. Bye-bye.
Bye bye.
Bon, t'as arrêté de...